This picture didn't start as a photograph. It started as a faint radio signal, hydrogen, inside a body. The scanner heard all of it at once. Left and right, front and back, fluid, fat, and brain, mixed into one wave. Then it worked out where every part came from. How? In this 4-part series, we'll look into how a scanner turns invisible magnetism into a picture and pinpoints exactly where you are. Each hydrogen nucleus has a quantum property called spin. It gives the nucleus a magnetic moment, a tiny magnet. Left alone, the directions cancel. But in the scanner's field, 2 orientations differ slightly in energy, and a tiny majority takes the lower one, about 10 in every million. That sounds hopeless. But one voxel holds so many nuclei that the sliver adds up to a real, measurable magnetization, and it doesn't sit still. It sweeps around the field, faster the stronger the field, about 128 megahertz at 3 Tesla. Along B0, magnetization is almost silent. The scanner adds a rotating radio field. If it runs too fast, the angle slips and one nudge can undo the next. At resonance, both circle together. The push stays in the same direction, so every cycle adds and the magnetization spirals sideways. Now the transverse moments begin in step. There some rotates past the receiver coil and induces a voltage. 2 relaxations begin together. T2 is sideways phase loss. The transverse sum and signal shrink. T1 rebuilds magnetization along B0 as energy returns to the surroundings. Different tissues run these clocks at different speeds. T1 weighted images usually make fluid dark and show anatomy. T2 weighted images make water bright, so edema often stands out. We can make a signal and hear it, but the mystery remains. One coil hears the whole slice, summed into one wave. There is no microphone per voxel. Position has to be written into the signal before we record it. Gradient coils do that. They make field strength depend on where you are. A matched radio band selects one slice. A brief gradient gives every row a different phase history. During readout, another gradient gives every column a different pitch. Sorting those pitches gives one shadow through the slice, not a complete picture. Repeating the measurement with different row phases makes the rows stop being interchangeable. The coil still hears one wave, but position is now fingerprinted into frequency and phase. Now comes the bridge. For one k-space coordinate, the scanner compares the whole slice with one stripe pattern. Multiply the slice by a cosine stripe and add every contribution. That is one real number. Repeat with the sine stripe a quarter turn later. That is the imaginary partner. Together they make one complex sample, including phase. As the readout runs, it records many of those complex samples. They trace one line in k-space. A stronger gradient, or the same gradient held longer, moves the measurement farther from the center. K-space is not a blurry photo, and its coordinates are not places in the body. They are spatial frequencies, patterns that vary slowly or sharply across the whole image. The center holds broad shape, most signal, and contrast. The rim holds fine boundaries and detail. Combine both, phase included, and one inverse Fourier transform turns frequency back into position. Change the gradients, the timing, or the reconstruction, and the same physics can film speech or follow blood oxygen fluctuations that only indirectly relate to brain activity. An MRI never looks inside you. It makes invisible magnetism carry an address, then does the arithmetic to bring the picture home.